In the previous video, we looked at how queuing works from the time a packet enters a router's ingress interface until it's transmitted out of its egress interface. But in this video, we focus solely on the egress interface's output queue because this queue is most important when network congestion occurs inside of a router. Default output queues are only used when routers are congested with packets. Cisco routers uses two default schedulers on its egress interfaces. On Ethernet interfaces, it uses FIFO queuing, and on serial interfaces, weighted fail queuing. The main difference being weighted fail queuing attempts to give all flows equal bandwidth rather than just processing packets in the order they were received. A flow is a group of packets that are transporting pieces of the same data and share layer 3 and layer 4 header information. In this example, an 8-year-old is sending an email reply to a classroom admirer. When she clicks send, her email is more than 2,000 bytes in size. Therefore, her email is being broken up into two packets because by default, networks do not allow packets to exceed the 1500 byte rule. In this example, we watch as the two packets carrying her email arrive to the router. Here, the first one shows the layer 3 information, and it shows the layer 4 information. And then it gets stored inside of one of the receive queues in the router. Then the second packet shows the same layer 3 information and the same layer 4 information. These two packets are both a part of the same flow. There are several types of queuing strategies and algorithms on the market today. However, we'll only discuss the ones listed here. In this example, we see the problems that would and could occur when FIFO queuing is used on low bandwidth interfaces like serial interfaces. In this example, we see two 1500 byte data packets followed by an 87 byte VoIP packet. As these packets wait to be assigned to the transmit ring, there's only one spot available on the transmit ring. The first packet, which is the data packet, will get that spot because of the first in, first out algorithm. The first packet is 1500 bytes in size and takes about 214 milliseconds to process. Because the second packet is the same size, it too will take 214 milliseconds to process. However, the VoIP packet can only withstand 150 milliseconds of latency. This example shows why on low bandwidth interfaces, FIFO queuing is not the best option for delay sensitive packets like VoIP. Round robin queuing was created to remedy the unfairness that exists with FIFO queuing. With this queuing method, packet arrival is of no consequence as the round robin scheduler attempts to treat all flows equally. In this example, the single default output queue has been broken up into 3 queues. Each queue represents a flow. In this example, the round robin scheduler dispenses one packet from each queue one after the other. The problem with round robin, however, is it doesn't consider packet sizes. Bigger packets still consume most of the interface's bandwidth when their queue gets serviced. Therefore, the fair queue algorithm was created to solve this problem. The fair queuing scheduler attempts to treat all traffic the same by taking into consideration packet sizes. In our example, we have the same 3 flows from the round robin example. This time, as the packets are serviced from their respective queues, notice that 3 VoIP packets are processed from its queue before one packet is serviced from the other queues. This is because 3 VoIP packets are about the size of one of the other packets serviced from other queues. And although the fair queuing algorithm does its job at making sure that flows get equal treatment when it comes to bandwidth based on their packet sizes, there are times when flows may need to be favored over others. This is where weighted fair queuing comes in and saves the day. One of the things that made weighted fair queuing different from fair queuing is the fact that it uses weights, and these weights allow it to show favoritism to one packet flow over others. The weight that it uses is the IP precedence value from quality of service. Packet flows with a higher IP precedence value will get more favor toward bandwidth than others that have a lower IP precedence value. However, if packet flows share the same IP precedence value, then weighted fair queuing will determine who goes first or goes next based on their finish times. And finish times are basically based off the smallest packet. Last, weighted fair queuing uses the IP precedence plus 1 bandwidth formula to determine how much bandwidth to give a flow that has a higher IP precedence value. In this example, let's assume that the packets from all 3 flows arrived at the same time. The first flow is a void flow and has an IP precedence value of 1, and void packets here are symmetrical and they're 87 bytes each. Flow 2 and flow 3 have an IP precedence value of 0, and their packets are variable. Because the void packets in flow 1 have a higher IP precedence value and the packet lengths are smaller, they have a shorter finishing time. Therefore, the weighted fair queuing scheduler will focus on flow 1 and begin to process packets from that flow first. The scheduler will continue to process these void packets until either another flow shows up with better finishing times and IP precedence values, or the queue is depleted. Now that the last void packet is being processed from flow 1, the scheduler turns its attention to flow 2 and flow 3, which both have the same IP precedence value. So here, the scheduler focuses on finish times. It takes the third packet from flow 3 first, and then it takes the first packet from flow 2, and then we have a void packet that shows up again in the IP precedence 1, flow 1 queue, and so therefore it gets preference again and it gets processed. The final queuing strategy we want to reference is the low latency queuing or LLQ queuing strategy. This queuing strategy consists of 2 queuing algorithms. One is priority queuing, the other is class-based weighted fair queuing. In the LLQ queuing strategy, the priority queue has priority over class-based weighted fair queues. Packets that reside in this queue go first. However, in order that the class-based weighted fair queues are not starved out, this queue can only send packets up to a certain amount of bandwidth. Once that bandwidth is reached, then the other queues are served. On the other hand, class-based weighted fair queuing is for less sensitive traffic. It is derived from the weighted fair queuing strategy, but unlike that strategy, it focused on building queues based on classes rather than individual flows, and packets that reside in its queues can use up to the allowed amount of bandwidth and use more if that bandwidth is available. In this LLQ example, queues have been assigned classes, and one class has been assigned a priority queue, the other classes have been assigned a class-based weighted fair queue, and the default class has been assigned a weighted fair queue. The priority queue has been assigned 50% of the interface's bandwidth. As void packets are being processed from the queue's clock is counted down towards 0. Once it reaches 0, the scheduler will move from the priority queue to the class-based weighted fair queues to service them. In this example, the call signaling class is serviced next. Notice how the bandwidth usage clock counts up to 25% because the class-based weighted fair queues can have up to their allowed bandwidth and more if available. The web class is next. It too is being serviced by the class-based weighted fair queuing algorithm and can use up to 25% of the interface's bandwidth or more if available. The final queue will be assigned the default class and will be done so automatically by iOS and will be serviced by the Weighted Fair Queue scheduler. All packet flows that have not been assigned a class will be assigned to this queue, and if there's any bandwidth left over, then this class will be serviced. In conclusion, software queuing is a tool that network administrators can use to manipulate packet flow in routers that have low bandwidth interfaces. And choosing the right queuing strategy will help ensure that the traffic that's most important will arrive at its destination in a timely manner.